Okay, the next talk is given by Professor Deliang Chen, who is August Rose's chair. He is from University of Augsburg. The title of his talk is The Important Roles of Modeling in the Development of Climate Science. Let's welcome.
Thank you, the chair, and also thanks the audience for coming. And it's my great pleasure to be invited to give this talk here in front of many scientists in the basic science. I'm from the climate area, which is I consider as actually both theoretical and applied. And theoretical in a sense, it's the climate science is based on physics basically. A lot of mathematics has been used. But I also show you that actually chemistry is important, even biology, and that the modeling has been very important in terms of the development or evolution of climate science. So basically, I will give you my personal reflection on how I see climate science has evolved and where it is going to be, and also what kind of role simulation modeling has played and will play in the future. By the way, if you don't know the University of Gothenburg, which is located in the city of Gothenburg on the west coast of Sweden, actually Sweden. And so this is how I see, and also many people see what is climate science. And many people see climate science actually as methodology plus geography. It's very classical. And as I will show you that it might be true in the beginning, but I think it's less relevant, this kind of definition or thinking or mindset, because I hope I will convince you that climate science has been evolving into something actually much more complicated. Not only including the natural sciences, but also including the maybe you could call social sciences. And one very important thing here, that is my key point here, is that I think what makes climate science a science compared to, for example, geography. And I worked a lot with people from geography, and we always discuss what is the difference. And one of the biggest difference for me is that we always try to predict, while the geography always try to describe or characterize. And to me personally, a real science is the ability to predict. And that's, I think, and also in the beginning, as I will also show you in the history, that climate science in the beginning is considered as a description of climate. So it's not really predictive. So I think that is a very important change in the history of climate science. And another big change is that in the beginning, it's really about atmosphere. And then people realize actually vegetation, land surface, ocean, for example, these are very important. And then later on, cryosphere and other spheres have been established. And the climate science has become a science of so-called Earth system science. And finally, there's something beyond that. That is, climate science is involving also a lot of societal elements. Yeah, because the development of science has been really driven by the needs of society, for example, climate change. And IPCC played a very important role. Technology is also, because this in the morning we have heard 2 talks at least focused on technology. And this kind of development cannot be underestimated because as you can see that actually climate science is also has been formed and will be shaped by development in technology too. And among other things, for example, AI, we will also hear more in the afternoon. And the politics also. And that is, of course, another topic, but it's very interesting, fascinating. I could give a talk. I'd love to talk about this also. As you know, climate science is not just physical science anymore. This is a pretty good picture. And many people, and especially people from physics, we say that we only interested in the climate system, sometimes called Earth system. And what we do is that we're studying the dynamics of the system, and we try to predict the status of climate system, for example, climate change. But if you look at the root of climate change, it is really driven actually by the energy consumption. And when we talk about energy consumption, about the GDP, the development, you have a lot of non-natural science dimensions. For example, you could talk about what is success. Is that money? Is that the development, as we have seen in Asia over the last decades? And just a large part, yes. But we know that there is some point of saturation, and also the development, especially economic development is not always a good thing, I would say. And in that, of course, we have a lot of like value, culture, education, etc. And so in that, you can easily see there are politics involved. When value is involved, there are a lot of, I would say, polarization also. And you now in the US is a very good example, as you know, that very, very different views from two president candidates, and in many other countries too. One is against climate change, and another one is maybe for climate change. And to put it in a simple way, it's quite opposite view. In science, we know that cannot be true. We only have one truth, and so that slide really demonstrates that it is not just natural science, especially when you have, when we talk about technology, for example, then vested interests are involved. So this is a slide actually I typically talk to my students when talk about evolution of climate science. And I could easily, just with this one single slide, I can talk 2 hours. So rather here, I think you are experts, and many of you know what has happened. So I'm just going to highlight a few important things, especially in relation to this workshop. And number one is that, of course, it has a long history. You see that Aristotle already wrote a book about mythology many years ago, 350 BC. But the real thing, I think, starts is that we have, from the 16th century, the Europeans have developed instruments to measure things like temperature, like pressure. That is very important because, as we also heard from last lecture, a lot of information has been connected. These are data. All science, most of the science, I would say, come from data, as you know, and logical reasoning, of course. So in climate science, actually, we can trace back to Alexander Humboldt, who is a German geographer, actually. And he, for the first time, connected a lot of data around the world and made the first map of temperature distribution, and basically defined also what is climate. The other things we don't have time, but I also want to mention one thing, that is another German geographer, Köppen. I think he has a Russian origin, at least a lot of connections with Russia, published, by the way, he is also related to Alfred Wegener, who invented the continental drift theory. And it's a quite interesting story, looking at how they interacted with each other in the history. But anyway, he actually created something we call climate classification, basically to put climate from time to to the space, and so basically made a link in time and space. And I think that is very interesting. But the view he had is that climate types or biome, basically vegetation types, animals, and so on, are actually can be classified into different groups, and these are basically determined by climate. So he actually developed a map of this kind of distribution. I just listed 5 big groups, and for example, B is the dry climate, and E is the polar climate. And what I did more than 10 years ago is that we took that system, but we took a different perspective. We said that action time is changing. It's quite interesting, and when people define climate in the beginning, they define climate as something static, not changing. So if now we have some data over typically more than 30 years, which is a time period which we use typically to define climate. And then we have this like 30 years, or 150 years, then we can look at the temporal evolution. And for example, that is a very simple way to see that the B climate looks like it's increasing. So the arid area in the world is expanding its climate. The E climate, of course, the polar climate is shrinking because of the increased temperature. And with that kind of view, you can identify black regions or transition regions where you will see a lot of change. Basically, these are the regions between two different climate types. And of course, a lot of other developments has also happened after that. One important thing is that actually in 1957, I will tell you that is launched by International Science Council. And I used to work, as I've told my colleague, I used for that organization for some years. In 1957, they launched something called International Geophysical Year. That is an amazing thing because International Science Council encouraged everybody and organizations, research institutes to do research, especially observations at the same time, intensively. Everybody understands or have seen the plot of the carbon dioxide in the atmosphere measured in Hawaii. And that is one of the biggest iconic data from that period of time. And I can tell you many, many stories about the importance of the data starting from 57, because it's really, I think, really made a lot of contribution to the development of climate science. And then another dramatic things happened in the 60s, 70s, and the GFDL and in the US, Princeton, and a few people actually started to develop a real climate model. I call it a real climate model because actually a very simple climate model has been developed much earlier. I will show you later on. But in the 60s, 70s, and especially Malawi was one of the first to develop a global climate model, including basic elements, the atmosphere, the land, and so on. And that is a remarkable achievement because he used computer simulation. And that work was rewarded a Nobel Physics Prize. And that is, to me as a climate researcher, I think is remarkable. And that's also why I'm very proud to be involved in the process to see this happening and to make this happen also. And a lot of other things also. I think one of the things I would say is also very important that 1979, we established a global research program. I will talk about this in the end when we talk about the future, because there is an international community talking to each other and planning and do strategic planning about climate science. That is, I think, something different maybe from mathematics. And I personally feel, because I have been working with people from different disciplines, I always encourage people to think about this kind of possibility to get organized. And because the community power energy is much more than individual or small groups. And then I think I just talk about one more thing, that is 95. We have a group of people, especially one atmospheric meteorologist or climate researcher, Paul Crutzen, and got the Nobel Prize. This is the first time a climate researcher got the Nobel Prize. He was rewarded for the discovery, actually for his very simple computer simulation of ozone dynamics with 3 equations, chemical equations, very simple. The model is very simple. In the beginning, it's 1-dimensional, then 2-dimensional. I saw the code, and because I worked with Paul Crutzen as a PhD student, and really understand how important computer modeling has been, because the other two was basically people who were doing experiment in the laboratory. And the three got Nobel Prize because the laboratory work support simulation. The simulation also, basically support the laboratory results. And then maybe just find one more thing, that is the IPCC. IPCC was created actually in 1988 by somebody called Bert Boning. I will have a picture to show him, because Bert Boning was the supervisor of Paul Goodson. He's a professor in Stockholm University, and I have the pleasure to be colleague with him for some years when I worked in Sweden. I started working in Sweden some 31 years ago. So, and IPCC AR6, that is the sixth report. As you probably know, that IPCC every 5 years about create a report, assessment report. So this is the IPCC AR6, and in that chapter, and this time I has been involved to create this history. We wrote a section about history of climate science, and basically describe what I just said. You see that we started with observation, and I think for people who are sitting here from mathematics, physics, everybody knows Fourier, and he's not only a great mathematician, but also he actually first did experimental work demonstrating the role of carbon dioxide in the atmosphere. So it's you see that in laboratory work, observation, and the development of model. That I think has been really played a very important role. But in the end, the model has been able to put all these theories and all these observations together. And that's why in this diagram, we basically show the Hawaii measurement data together with global mean temperature. You can see that to prove this change of temperature is caused by carbon dioxide takes the modeling, not just the experimental work. But I have to mention one more person here, because this is a guy, a Swedish scientist called Svante Arrhenius. Already in 98, he has actually developed what I would call the first climate model. And if you are teaching climate modeling, you are starting with something called a zero-dimension global climate model. That is his model. So he took the whole Earth and look at the energy budget, and then come up with the temperature result. And then he see the greenhouse effect. And then he doubled greenhouse effect, and then to see how temperature react to that. That is today we call climate sensitivity. And he came up with a number that is around 6. So if you double carbon dioxide, the temperature will be increased by 6 degrees. And today we know from IPCC work that number should be around 4.5 degrees. So it's not far away, and that is amazing because he used a very simple model to do that. And this is a picture of Bert Boning. I show him because he's a really respected colleague, and also he's the father of IPCC. And also he's the father of WCRP too, by the way. So the WCRP would not be created without him. And so we can see that a few individuals can play a huge role also in the history of climate science. Of course, there are many, many things we could talk about, but I just want to highlight this a few individuals and also people who has made a tremendous contribution here. By the way, so this is the meeting, the room where we had the decision meeting about Nobel Prize 2021. So once we made the decision inside this room, I had the honor to go out to talk to the Swedish Central Station, TV station, because Swedish journalists are the journalists who got news first as a good tradition. So I had the honor to talk to him about why we give the prize to these 3 climate scientists. And also there were Chinese, later on there were Chinese also, journalists there in Stockholm. So I want to move on a little bit about the new developments and also the future directions. And conceptually, I think this is a very good diagram summarizing everything I just said. That is, we recognize now the climate system is not only just dynamics, it's not just physics, in other words, but also chemistry, also ecosystem. So we have ecology also. And all this interacting with each other. And of course, we have also external forcings, drivers. And I think that is important. That is, today we see human as an important driver. And I think I have a picture to show you that focusing also have another very important contribution. He basically defined something called the anthropocene, saying that we are living in an era where human activities are really a big player to change the system. This is what we see in global warming and climate change, etc. Of course, you also have natural forcing here. So what we do is that we try to develop actually models here. And quite complicated ones. I was with physics, chemistry, biology interacting with each other. This is of course very simplified diagram. And then we try to also to identify the forcing or determine the forcing. For example, we know the sun is changing all the time. We know that we have occasionally volcanic eruptions, which is one of the major natural forcings. And then this is difficult about human activities. And we know that greenhouse gases is one. We know that land use is another. But there are other activities such as now we are living in Beijing, for example. We have quite pleasant temperature inside. Why? Because we have air conditioning. And to do that, we need a lot of energy. And in winter in Beijing, it's cold. If you have been in Beijing, you know that. We have also quite a good temperature because we use energy to heat the house. Again, a lot of energy. And actually, for the city scale, the energy is tremendous. When we talk about the doubling of carbon dioxide, we are basically adding a few watt per square meter to the system in terms of energy, like maybe say 2.5 up to 4 watt per square meter. But in Beijing, in a city, we have anthropogenic heat release around 300 watt per square meter. This is the average. The peak energy we are releasing could be up to 800 watt per square meter. 800 watt per square meter, which is approximately the energy from the sun. So you can see the human impact. Of course, this is quite local scale, not global scale. But still, you can see that the human activities is huge. This is also why I think we pushed the climate system into something we call Earth system science. And in 2010, I will tell you a little bit of the story in the end. And why we do that is that I was a leader of a process called vision process to look at what's going to happen next 20 years in climate science. We said that we have to talk about Earth system science. And also we try to identify Earth system as something, including, as I said, physical, chemical, biological, and also with human or societal components. I think this is conceptually, this is a big revolution that we really move into something, what we call post-normal science. I don't know if you are familiar with the philosophy of science or history of science. And Thomas Kuhn has defined something called normal science. And then he also defined something called post-normal science. So climate science is typical post-normal science because you have the societal or social components involved. And the purpose is very important. Also, we are not only looking at the dynamics of, dynamics of the Earth, but also we're also looking at the impact on human. So basically, in the past, our disciplinary work is like everybody's taking one piece of the puzzle, and basically we cut off a lot of connections between the pieces. And what we do with Earth system science is that we try to put all the pieces together. Of course, that is difficult. And what we are trying to do is that we put into computer, of course. And it's very difficult into the other ways. Here you see again the importance of a model. You need to have a model to do that. Otherwise, it's very difficult. So we have a lot of opportunities, I think, in the future that we know that climate has played an important role. And also we know that climate science has been transformed into something called Earth system science. That is going to continue because the human pressure on the Earth system is continuing. And also we need to have not only identify problems, but also to identify possible solutions. For example, climate is a very good example. Environmental degradation is another. Basically, the idea is that when we integrate different components, we strongly believe that the whole is much more than individual parts. And that's why we push all disciplines together to really deliver what the society needs. And into that, of course, we need to have modern work. I did not have any slides, but I think many people understand. We have weather model, we have climate model, basically, solving the equations, Navier-Stokes equations, and with all the 5 spheres of the system: atmosphere, ocean, biosphere, etc. But also, you have laboratory work because there are some processes which we don't understand well. So we still need laboratory work, and also we need to have field measurements. And the data is still the engine to drive the science. And I think the last point here also, which I want to highlight, is that actually the new technology, not only AI, but also including AI, can be a very important part. Why is that? Is because if you look at history, not only in science, but also history of human society, you see that technology actually is a transformer. It's really changing how we work, how we think, how we do our things. Looking at today in a society, everybody's iPhone or a smartphone, this technology, the invention of this technology has really basically changed how we live, how we interact with each other, and both positively and negatively, I would say. But one thing is clear, that it has a strong impact. And that is the case for AI and other new technologies for climate science. For example, we could think about it. This morning we heard the technology that can be used, optical cable, for example, can be used to detect structure changes in the Earth, for example. That can be useful. In atmospheric science, we know that by analyzing the GPS signal to your iPhone or to your smartphone, you can get some information about atmospheric moisture. So all these are technology. If they are used in a smart way, it can be helpful. And so I think there is going to be a lot of development in all this. In what follows, I will give you one example of one AI system I personally have been involved in, and the development of a system called the Fuxi system, and mainly developed in Shanghai, Fudan University, and also there's an Intelligence Institute, Research Institute in Fudan. The last point, before I'm going to do that, last point I want to make is that international collaboration is hugely important because all these need a lot of collaboration, not only in terms of people's exchange of ideas, but also in terms of infrastructures. For example, if can you imagine that we have atmospheric science. I would say if you compare atmospheric science with ocean science, probably atmospheric science has been more advanced or has been developed more. I think one of the reasons, there are many reasons, one of the reasons is the observational network that the atmospheric science has been developing. In ocean science, we know that it's only after IGO has been put into place that we have started to have a kind of quite good measurement. Before that, it's very sparse measurements, which of course will be limiting to the development of science. While in the atmosphere, we have like temperature, for example, temperature measurements every 3 hours since more than 100 years ago. We send this measurement to each other. And today it's called the WMO, the World Meteorological Organization. In the history, it's called IMO, International Meteorological Organization. But anyway, more than 100 years ago, even without the internet, we sent by telegraph the measurement to each other. So we already have very good measurements over 100 years in the atmosphere. The ocean is starting, and other fields like ecology is starting. You know, we talked about human component. That is not really studied yet, in my view. So we have a lot of potential. But now I just move on using my remaining time to talk a little bit about one example of the AI in the climate science. So when we talk about why we need AI, of course we have to talk about why what kind of limitations we have with traditional climate models. And we have some climate model experts here. We know that that field has been developed pretty well. And the model is very sophisticated, but there are some limitations. I just listed here. One is that the resolution is limiting. And typically today with IPCC work, global models has a resolution about 100 kilometers. Can you imagine 100 kilometers? So basically it says the climate here and in the city center of Beijing is the same. And probably you see the limit. Temperature is actually pretty okay because the temperature is still very large scale. If you talk about precipitation, sometimes just cross the street. One side is raining, the other side is not raining. And then not to mention that the rain here and in Beijing city. So that is a big limitation. The other one is that we have a lot of, because of the coarse resolution, we have to parameterize. You have to find empirical relationships to resolve or to try to find solutions for some processes which are not resolved by the model. And this kind of parameterizations is a huge source for errors in the model. And then in the simulation, especially in terms of prediction, we try to integrate observation with modeling. And we use something called the data assimilation. And also in terms of prediction, you all know that the climate system is a chaotic system, and the weather especially. When you try to predict the future weather, you get different answers when the initial condition is slightly modified. So you need technology to kind of to get what we call ensemble prediction. So you have many different predictions, how to combine them. There is also a lot of uncertainties, but we really don't have a very good method, I think. And so how AI can help? So at least I will hear your opinion here because we have some AI experts here. And this is what I can think so far, but it may be more. I think AI is a very powerful tool to do the pattern recognition and identify, and also do the classification. And classically, we in our field we use like things like UF, empirical orthogonal function analysis, something called the PCA, principal component analysis, depending on how you see it. But AI is much more powerful also because all these techniques like UF and PCA has some mathematics constraints which are not really physical. So AI typically can really solve that problem. And the other thing is about scaling. And I think AI has a potential to be able to provide a powerful downscaling, for example, tool. Sometimes even maybe upscaling too. When you do the parameterizations, you can put into the model. So to build a bridge between different scales. And I have been doing a lot of downscaling work myself, so I know that the limitations of the classical method. The classical methods basically are based on regression method, and many of them are linear method. So I think AI can really do a good work. Of course, if you do this kind of empirical downscaling, you need data. But once you have data, actually it can do a very good job. And it also can actually replace some of the parameterizations or maybe improve the existing parameterizations in the model, which has been actually tried and quite successful. What I want to highlight here is that, I'll give you one example, is that it can improve weather and climate prediction. And the climate, not so much work has been done, but the weather, I will show you, has been done. And also it's moving towards climate scale also nowadays. And finally, I also believe it can also provide a very useful tool to do the ensemble prediction, because now you have, it's basically a huge amount of data. In our field, we have many models, and we run models many times. So this huge data set there. And it's very difficult to use traditional method or for human to develop a good method to do the ensemble prediction. And so the biggest problem, I think, with the traditional model is that it cannot easily scale up with observational data. And so that the AI can be helpful. And also traditional model is really taking a lot of computing time. And finally, that predictions such as MJU, which is a phenomenon, I will have a picture show you what it is. It's very difficult with traditional weather forecasting model. So this is what we have. Of course, this slide was provided by my colleagues in Shanghai, and which might not be so complete anymore. I just realized this morning. But anyway, it listed what we have until, say, a couple of months ago. And you all know that actually Pangu weather and model got the prize this time. We have another prize winner here, also working with AI. And so there are also a number of other models in terms of the time when they were released, and also with regard to the lead time for predictions. So if you look at predictions, around 10 days, that you have several options here. And one reference we typically use is something called high resolution prediction from European Center for Medium and Long Range Weather Forecasting, ECMWF, which is usually taken as a reference. And I will show you some slides taking ECMWF's model as a reference, because these are predictions from the traditional models. And Fuxi has a kind of base model, and then it also has several variants focusing on different time scales. So the base model has such an architecture of model structure. And I'm not AI expert, so I cannot explain to you more details, and just trust my colleagues that what this is about. And so the key here is, of course, something called a U transformer. Then the Fuxi-based model uses something called a cascaded model to actually fine-tune the different lead time predictions. So it has a short term, it has a medium term, it's a long term. So there are some overlapping. So the strategy is that you first have an overall tuning, if you want, and then you tune them or optimize them with regard to different time scales also. Okay. So if you look at the 10 days forecast accuracy, you can see that actually Fuji and GraphCast in that case auto performs ECM doublets, finding the solution up to for the 10 days. And then within 7 days, actually Fuji is comparable, and but it's better than GraphCast up 7 days. So overall, Fuji is performing well compared to these two reference. It's also comparable. I don't want to go into details, but it's basically all the graphs showing that even for 15 days forecast, it's quite comparable to ECMWF. And but after 9 days, it's slightly worse than ECMWF. So there's still work to be done. And also Fuji has developed a version for extreme weather, because as you know that most models actually doing pretty well for the smooth conditions. Extreme weather requires abrupt changes. So what they did is that they introduced something called diffusion here, and then add some noise, and then look at the prediction and try to optimize not on the mean conditions, but also optimize on the extreme events. It has been demonstrated that it is doing well actually compared to, for example, ECMWF's model. In this case is for the tropical cyclone, we call it typhoon in China. And most of the predictions are actually better in the Fuji model than in the AR5, which is a reference. So I think I'm close to the final slides. Just say that it also has a version especially targeted on something called S2S time scale, that is a subseasonal scale. Because if you look at the scale of the forecast, and that this is a typical weather forecast, and this is typical seasonal forecast, and sometimes we call it climate forecast. And in between, we call it prediction desert, because the scale is very poor. So there's a challenge there. And Fuji model has tried to solve this problem by adding some perturbation into the AI system, and then do some basically training, optimization, and try to get better predictions of this time scale. If you look at the test that we have been able to show that it has a better performance than the ECMWF sample and prediction. So this is MGO, and basically it's a tropical phenomenon, and with a time scale 30 to 90 days, a lot of strong weather conditions, especially in Asia, are caused by MGO. So if we can predict MGO well, then you will be quite sure that you have a success in the weather prediction, long-term weather prediction. So that is what this system has been tried to optimize to. As you can see that now compared to ECMWF, Fuji S2S system has basically extended an MGO prediction scale, because typically we take 0.5 as a threshold to show that if you have a scale a lot, and you can see that here. Sorry, always press too much. So here you can have a few days and progress. That sounds not so good, not so many days, but actually you should know that it took the community like 20 years to achieve something similar. So with AI, I would usually to joke, with AI you can achieve this within 1 or 2 years. Yeah. So maybe I'm looking forward to the next 2 years. Maybe somebody can even do a much better job than that. And also we look at the 2021, there's a big flooding event in Pakistan. We did a hindcast. We try to recover or we predict, and it looks like the FTSE system is also doing well in comparison to ECMWF, which is blue, and the black one is the observation. You see that the FTSE model is doing well also in this case, but of course we know that we have to look at many cases to see that. So finally, I'm talking a little bit about future, and so I have the pleasure to be the head of International Science Council for a couple of years, which actually lead all the we call the global change programs, where scientists are organized to look at the environmental changes, especially climate, with WCRP as the first one, as I mentioned before. And also we have developed something called IGBP, which is focusing on the land and the biosphere, and then the biodiversity. And later on, there's also a mention or addition to the human dimension that is very important, societal component. So when I became the head of ICSO in 2009, and we basically said that we have to look at the organization structure and also to develop new strategy. And so we basically create a new program called Future Earth, and try to, as I said before, to add the post-normal science component, basically the transdisciplinary science. So we emphasize on co-design and co-production with stakeholders, with society, in other words. And this is a vision paper we published in Science 2010. And basically, this is also the concept paper for Future Earth. If you're interested, you can have a look at the Future Earth, which is at the moment the largest, I would say, Earth system science-based research program in the world. And in that vision, we basically outline 5 we call the ground challenges, big challenges, science challenges, which I think will be guiding us into the future. And what we said is that we have a huge challenge to do forecasting. As I said before, prediction is the characteristic, most important characteristic of any science. In that area is especially important. So how to do prediction, how to improve prediction is going to be still the important one. But of course, with that, we say that it's not only the prediction of physical variables, but also other variables, even including social, societal variables. That is really a challenge. We usually believe we have enough data, but actually we don't, especially with regard to socio-economic data, ocean, for example, cryosphere, the polar regions. These are regions we don't have really enough data. So we still need to develop observation systems to get more information. And then there's another thing that we see, because this is a complex system, so we are going to see a lot of nonlinear behavior, such as tipping point. You have heard the term tipping point. I just actually gave another talk in another workshop about tipping point. And we see that we have such kind of behavior in the system. And to predict this kind of things probably is impossible, at least today. But we should be able to kind of figure out the dynamics behind the tipping point system. And also can do some expectations. We can be maybe expecting some of the part of the system can be having this kind of behavior. This is of huge importance for society. And also that responding, that how we basically mitigate and adapt to the changes is also very important. Here you have the governance and the international cooperation are very important. And finally, innovation. I'm sorry that this picture is not what I want, because this picture gives you the impression we're only looking at the innovation on technology. So no, we also want to have innovation in society, for example, how we organize our society. If you are good in reading the co-authors of that paper, and we have actually Elinor Ostrom, the Nobel Prize winner for economics, as a co-author. She actually emphasized a lot when we read this paper. This is not just technology, but I'm so lazy to replace this picture, but this picture was selected many years ago. So that is my vision, or I hope, the future of climate science. That I think we are going to strengthen our prediction capability, especially on the seasonal and the decadal timescales. I emphasize that because we typically do climate projections for like 100 years. And these are important, of course, but also in society, people always say that we need information about 10 years, 20 years. This is basically for the infrastructure development. And seasonal prediction is also very important, especially in Asia, I would say. Then we also have to develop different products for prediction, for different purposes. And here in China, actually, I think China is doing well because I have seen a lot of quite innovative products. For example, in Beijing, there is an index for washing the cars. If you want to wash a car, you should not wash a car when it's a huge rain is coming, because when it's raining, it's going to be dusty again. So you have to maybe wait. And so you can, a lot of, for agriculture, you can think about for medical science, for diseases, prevention, a lot of services, we call it climate services, can be developed. So this is also a huge area of development. And I also emphasize the importance of regional scale and local scale, because we typically talk a lot about global warming, global change, but actually what's impacting you and ecosystem is very local. So we need this type of information. And downscaling is going to be important. So developing the downscaling technology is very important. And finally, this is really a system science. We need to cover quite different types of dimensions, and especially the human system. So with that, I thank you for your attention, and thanks.
Very impressive talk. Any questions or comments?
Thank you. Very nice talk and sharing your insights. And it's good to see that the FUSI team is put their efforts in extending the forecast lead time, not only for the weather timescale but also subseasonal timescale. So my question is that to achieve or to extend the forecast lead time beyond the weather timescale. So what's the detailed strategy of FUSI to move forward for their further development of their FUSI model?
Very important question, and I have not talked to my colleagues so much beyond the subseasonal timescale, so I can only share my own view on that. And actually, we will have a meeting soon to sit down to talk about this. And we all know that basically we have two types of prediction. One is the initial value prediction, the weather. The other is the boundary layer, and the subseasonal is kind of combination, I think. And then if you're going beyond that, main is a boundary value issue. And for that, I think you really have to think about the different components in the climate system. And you have to go really beyond, as I try to say here, not just the atmosphere. And ocean is important, of course, but also the biosphere, which we tend to forget. For example, vegetation is changing, actually. But in most of the climate models, vegetation is not that dynamic, or at least not dynamic enough. And the other thing is actually the water, I think, especially in a deep soil. And that is coupled to, of course, the ecosystem. And we know that all the climate model today has a soil which is 2 meters high, about. And many of the things like heat waves in Europe, we see the differences between different countries. And but if from atmospheric science point of view, they should be the same. But the difference is really the soil. That in countries where you have a lot of forest, the heat wave typically is much less severe because the forest can extract water from deep soil. And so this kind of conditions has to be incorporated, I think, into the thinking. And then maybe
do you think that the kind of coupling between Earth components with different timescale can be achieved by data-driven model?
And I think we need to do both. And on one hand, I think in long term, we need to develop the traditional model further. And for example, by extending the soil layer. And that is one way. I think they are doing that. But this is quite a slow process, we know that. So the other way, I think, quite a quick and dirty way, because AI is not always explainable. I say dirty. But actually, we can, I think with some process understanding, we can do AI and because you have so much satellite data nowadays, remote sensing data. If we tap into this resource and combine with AI, I'm pretty sure we can increase at least in the short term and the scale on the climate scales.
Okay, thank you. Any questions or comments from the audience?
Okay, thank you for your very nice presentation. My question is about the AI application. As you know, there are larger uncertainties in the projection in the 100-year scales. I don't know if the AI can help to reduce these uncertainties in the climate projection. Thank you.
Thank you for the very good question. I'm sure the answer is yes, because as you know that we, at the moment, we also summarize this in the AR6 report that we typically try to use the past observations and the emergent signal from different models to constrain or to reduce the uncertainty. And I think AI can help, and because emergent constraint is very simple in regression method. AI should be able to do a much better job if there's a non-linearity, for example. Because at the moment we just use the linear part of the signal, the trend basically. And the other thing is that we typically only do in one dimension at the moment. It's just, for example, for temperature, use temperature. But with AI, you can maybe use multiple dimension and then with some combination of different signals. Because climate change typically is not just one single variable problem. It's combined with different variables. So there should be some signal. But I don't know how to do it. Maybe we we have experts. And we hope that collaboration with AI expert and climate scientists, I think, should help.
Okay. And are there any questions or comments?
Can your model explain the so-called ice time of the Earth?
And time, what is that?
I mean in the
isotopes.
evolution ice time.
Ice time.
Yeah.
Ah, you mean ice age.
Ice age.
Okay. Okay, ice age. Yeah, of course. And very good point. Climate model has been used to simulate past change. Ice age, a long ice age, or interglacial, we call it, has been a very good test to see how the model has been working. And on that time scale, the driving force is mainly natural, and also mainly the solar radiation, and of course combined with greenhouse effects. So if you put all this forcing into the model, we basically can reproduce the ice age and long ice age. No problem. The model has been pretty good doing that.
Okay, any questions or comments? Okay, let's thank for Professor Chen again. Okay, thank you so much.
Thank you.